Alright, welcome to weeks 10 and 11. We'll be working more closely with the RCX inputs this week, establishing an understanding of two types of sensors we'll use to control our fish tank system. We'll also be applying the heating and valve operation ideas to the actual control of the temperature and salinity characteristics of the system. Let's review our progress so far. We've explored the following. The RCX programming concepts that we'll apply and expand on as we move forward. Also, the motor and pump characteristics will be applied this week, particularly the flow rates and their influence on this week's work. And then the electrical switching and power ideas will be needed to apply our new sensor experiences to the system operation. This week we'll focus on the temperature sensing and temperature control. The teams will complete a calibration of the sensor and then apply the math to predict and confirm the heater's ability to raise the tank's temperature. Next week we'll focus on salinity sensing and salinity level control. Teams will complete a similar calibration, practice the calculations for mixture changes, and practice controlling the salinity level. Next steps, after this group of activities, teams will begin working on their final programming controls, testing, and working on describing the system as they understand it. Let's discuss general sensor characteristics. First is accuracy. So accuracy is a measure of the resulting measurement's value, how close that value is to a true value. So in this dart example, the true value is going to be considered the bullseye on the target, while the mean value of the thrower's attempts is going to be the measured value. Okay. The left side thrower here is very consistent with all the darts landing close together. The right side thrower is less consistent, and if the accuracy is a measure of how close the mean is to the true value, then the thrower on the right is actually more accurate. Their mean value is closer to the true value, or in this case the bullseye, and it is a more accurate chance. So essentially this thrower has a greater chance of actually hitting the target, while the thrower on the left, although has other characteristics that are good, it's less close to the actual value that we're looking for. For our temperature system, the temperature version of this might look like the sample shown here on the right side. So here's the thermometer and the true value is shown. If we're taking measurements, and so the measurements, say on the left hand side of this line, are close together, this might be similar to the thrower whose measurements are close together. On the right side, the person taking these measurements is less careful maybe, or maybe the variation in the sensor reading is moving more. This example shows that the right side, although has a lot of spread, would be closer to the true value, while the left side less spread out but farther from the true value. Again, the RCX will display the measured value for our temperature readings, and the true value will be measured by a commercial thermometer. Okay, let's talk about precision. It's a measure of how repeatable an example is, and so the spread of the darts thrown is an example of how precise the thrower is. And so the left-hand thrower appears to be very steady with a spread that's very small, represented by the red arrow, while the right-hand thrower is all over the target and the spread is much wider. And so if you compare these two throwers, the thrower on the left is much more precise, while the thrower on the right is less precise. Similarly, the spread of readings on the thermometer example here, the spread is much more broad with the person on the right, and it's much smaller with the person on the left. So the person on the left would be more precise, or the measurement here would be more precise, while the measurement for the right hand side is less precise. For a single temperature, it's important to consider that a measured value is the same each time a reading is made. Two other concepts that come into play is repeatability and reproducibility. These are tied to precision. High repeatability indicates that the measurement is consistent over short periods of time. So if you're watching the measurement display and it doesn't vary much, it's more repeatable. Reproducibility indicates that the measurement is consistent over long periods of time. So if you use the same equipment and use it to measure the same variable at the same conditions, that would be reproducible over different situations in different periods of time. Alright, so let's look at discrimination as another sensor characteristic. It represents the minimum detectable change in a measurement. And so, using our dart example, the target shows a total of 11 shots. One pair begins to overlap and would be harder to distinguish from the others with any more overlap. In reality, 12 shots were fired at this, so 12 throws were done, and the discrimination might be described as some function of the diameter of the shot. So if the diameter of the shot is large, it might be more difficult to determine if there were more shots or less. So in our temperature system, we have to have a controlled temperature sample that can be very precisely controlled and kept the same. The discrimination would be demonstrated by changing the temperature of the sample very slowly and identifying what temperature change creates a change in our sensor. In our case, this would relate to how much heating and cooling it would take to have the display change. Sensitivity provides a general relationship between the input being measured and the output measurement. It can be directly related to graphical relationship of the true values and the measured values. The ideal examples shown here demonstrate the differences between changes in sensitivity. A slope equal to 1 indicates that the direct relationship is measured and between the measured and true values. A slope less than 1 indicates that the measured value changes more slowly than the true value. And of course, slopes greater than 1 indicate that the measured value is very sensitive to change and shows small changes more easily. With all the sensor characteristics and comparison of empirical data is necessary. For temperature and salinity sensors, you'll gather data and observations that should allow you to quantify and describe these characteristics. Without this, we might rely on measurement that is inaccurate. Knowledge of this relationship allows us to plan for the true measurement desired in our system. Sensitivity is the key characteristics we'll be exploring, but you should observe and discuss the data and possible relationships to accuracy, precision, and discrimination. Sensors can be made to adjust for nonlinear elements and produce linear results, and so we'll consider some of these along the way. Here's a more practical example of your experimental data for temperature sensors. The data shows a directly proportional relationship between the water temperature and the RCX displayed temperature. All right. The correlation between the data points and the curved fit line is very high in this case, and so this R squared value represents the correlation. Your team should also discuss, when you've seen your own data, the accuracy, precision, and discrimination concepts. Ideal sensors, of course, again, have a 1-to-1 ratio. This one, the sensitivity, happens to be less than 1, and so this 0.8436 indicates that a single degree change would result in an 0.84 degree change in this. The offset in this formula y equals mx plus b is the y-intercept, also clearly shown on the graph here. This indicates that even though the temperature might be 0, this RCX display would display a value that is 3.4 degrees, roughly. So the good news is, for most sensors, the electronics and internal microcontrollers are generally designed to accommodate these discrepancies and make the ideal sensor readings equal to the true value. It's fairly simple within the electronics to subtract the offset value and move the line down. And it's also fairly simple to multiply by a new constant value to change the slope to return the slope and sensitivity to 1. Okay, so heating and cooling are key concepts in all disciplines, especially as they relate to transfer of energy. Controlling temperature of manufacturing processes, building environmental controls, or managing the heat dissipated from a computer processor require application of these ideas. Heat capacity is a characteristic for any single object. Heat capacity represents the energy required to change the temperature of an object by a chosen amount. The units, of course, are given in joules per degree Kelvin, typically. Specific heat is a more useful concept. It relates directly to the mass of the object. So this is empirically determined and identifies how much energy is needed as a function of both mass of the object and the change in temperature. So this is the formula we'll be manipulating. The heat energy needed to change a particular mass is equal to the product of the specific heat of the material, the object mass, and the desired change in temperature. The temperature can be in Kelvin or degrees C in this application. And so in this example, the specific heat of water is 4.1813 joules per gram degree C, and the formula, if you want to know how much heat needs to be added, then you need to multiply the specific heat times the mass of the water times the change in temperature that's desired. Here are a couple of typical examples. So water for tea, if you're not sure how much heat it takes to raise the temperature from room temperature to 100 degrees C, let's take a look at that. And so in this case, if it's about 470 grams of water, about 500 milliliters, we want to raise it about 77 degrees C or degrees Kelvin. Room temperature is about 23, boiling is about 100, and so if we apply these ideas and the specific heat, we'll get 152 kilojoules is necessary to raise the temperature of water for tea. Now another example would be more realistic for us. If you have 1800 joules of energy that are going to be added to a tank of water through a heater, how much temperature rise should be expected? And so if we rearrange the formula for the change in temperature, identify our known values, 1800 joules for the heat going in, the mass of the water is 150 grams, and again the specific heat for water is provided at 4.183 joules per gram degree C. So for this amount of water and the amount of energy input, you should expect a 2.87 change in the temperature of the water. So let's move on to the salinity sensor. Measuring the salinity of a water sample is typically done by a more direct method. The percent saline of a sample is generally defined as the mass of the salt divided by the total mass of the sample of water and salt. And so in chemistry, a water sample would be weighed and then evaporated, and the mass of the remaining salt would be measured. And so that would give you a very practical example of how the measurement of percent saline would be determined. Now the good news is electrical properties of materials or systems are often used to create measurements that can be related to a desired measurement. And so in this case, the free electrons in the salt will allow current to flow through the water more easily. So as the salt solution varies in the level of salinity, the number of free electrons varies. And so the solution essentially becomes a variable resistor that changes with the changes in salt concentration. And so sensors can take advantage of this changing resistor and create a signal that can be displayed and used as part of a control system. Here's a quick overview of the salinity sensor. We'll be treating it much like a black box. We won't need to know what's going on inside of it, but we will need to know how it operates. And so again, the salinity sensor is going to be the tube that water passes through, shown here in the image, and the two stainless steel probes that have been pressed into it will act as our anode and cathode. And so with the ions in the water in this sketch here on the right, the ions in the water allow electricity to flow more easily and change the resistance of the water. And so the free electrons increase the conductivity and lower the resistance. So that resistance change becomes part of a small circuit that creates a pulsed waveform similar to what we were working with when we were looking at the RCX outputs. So this waveform will change, its frequency will change as the conductivity changes. Now another small circuit that you'll see on the breadboard when we apply those in week 11 is there to change that frequency into a voltage. And so we have a frequency to voltage conversion circuit, and then finally there's another voltage to voltage circuit that acts as a buffer. Sometimes electronic devices don't, when you plug them together, connect them together, they don't interact well electrically. And so the voltage buffer allows us to connect the output of our sensor into the input of the RCX. Let's take a quick look at the salinity calculations. Again, this is pretty simple stuff, but let's give it a quick review. So we're going to start primarily with deionized water and our sodium chloride solutions. So if you're just going to make a sample from salt and water, it's fairly straightforward. The mass of the salt divided by the mass of the salt and the deionized water. And so an example of this would include if you're going to make a sample of water that's similar to the ocean, which is about 3.5% salt, the mass of salt that would be needed for a 500 milliliter sample of water can be found by rearranging that formula somewhat. And so we rearrange and solve for the salt, and enter the percent salt that you desire and the total mass, and you end up needing about 18 grams of salt. It's actually quite a lot, when you see when you see and taste that. Alright, so let's look at another one. This is more like what we'll be doing in class, mixing known solutions. And so a new solution would depend on both contributing solutions. So solution 1 is going to have its own mass and percent saline calculation. Same thing with the second solution. The combined solution becomes the mix of both. And so if solution 1 is a 3% salt and has a volume of 425 milliliters, and solution 2 is 8% salt and has a volume of 125 milliliters, what's the percent salt in the final solution? So the salt contribution from each sample, 1 and 2, is 12.75 grams for the first and 10 grams for the second. So you add those up and find the total mass of the salt and the water at 550 grams, and you complete the calculation for the final solution and you get 4.13% salt. And so that makes sense. We started out with 3% and we added not an equal amount, a smaller amount, and so it should have risen not a lot when you add an 8% salt solution. This is an example you'll be doing in class and in the laboratory. One of the last items that will be important is valve flow rates. So we did activate the valves in the previous week, but this week we'll be during week 11 we'll have to make sure and understand how much water will flow. And so you'll be activating the valves shown here and measuring the flow rates that they can create. And so gravity determines the flow rate, and so does the size of the tube. And the RCX program will control the valve. So once you establish a known flow rate whenever the valve is open, you can determine how long to leave the valve open to add a specific amount of water. And so the DI and saline reservoirs or tanks that we'll be drawing water from will help us control the salinity, and additions to the tank will also influence the temperature within the tank. So the system becomes a little bit more complex because as we add water, that temperature in the tank will also change. Of course, the purpose of adding the water is to modify the salinity to the desired level. So the two control systems will have to work together. So let's talk about one more thing before we wrap this up. Let's talk briefly about sensor limitations. So both sensors we'll use have limitations of what they can measure and display. How high the temperature can be, how low the temperature can be, how low the salinity or how high the salinity can be done. So this example shown here is data from the salinity sensor. The blue dots shown here is the data were collected and graphed, and so as the data approached 100, the readings stopped changing. Looks like it got to about maybe 98 or 96. And so up until that point, the data is fairly well behaved, and our sensitivity data is going to be show a very nice curve or a nice straight line for our data. But beyond this, this is the not a usable range, because even though the salinity may be going lower, we can't get a reliable reading below this range. Same is true when you cross 0. The RCX will only display from 0 to 100, so once the salinity goes beyond the values shown here, we won't be able to measure it effectively. And so this is a limitation of the useful range of the device. So make sure and consider these ideas when you're looking at your data for both your temperature and salinity calibration curves. So that's primarily the stuff that we'll be working on this week. We'll be able to answer any questions you want as you go through the process.